We're going to talk about functions of two variables, actually eventually functions of more than two variables. But I mean, the course is multivariable calculus. So think about this. We've got a function z, which we think about as the height given above a point, an xy point on a grid. So our example is z is equal to sine of xy. So that looks like this. Now z is equal to the sine of something. So the biggest z could be as 1 and the smallest z could be as -1. So you can see this thing kind of waving up and down, trapped in between 1 and -1. If I were to take a slice of any of these things, now by taking a slice I mean let's just look along the slice where y is equal to 3, let's say. So to do that, I'm going to go and my viewing window is -3 to 3, but I'm going to change this to in the y's like 2.9 to 3. So I'm only going to take a small skinny, and there it's the sine wave. Yeah, I basically made y equal to 3, and now I'm looking at the z is equal to sine 3x. So regular sine period of 2 pi divided by 3. If I were to, I'm going to put this back. Let's take a level curve slice in the z, because that'll be interesting. So I'm going to take a level curve slice in the z where z is, like, where are all the places where z is 0? Now, it's the sine of x times y, so the sine of it, if x times y is any multiple of pi, you're going to get 0. Let's see what that looks like. So to do that, I'm going to take I'm going to tighten in my window here from -0.01 to 0. So these curves are places where well, this must be the place where x is 0 and y is 0. If x is 0, so all the way along this line where x is equal, no, where y is equal to 0, the function's at 0. Where z is, or where x is equal to 0, the function's at 0. These curves here are like, this is where x times y is equal to pi, let's say. So y is equal to pi over x. That's what I'm seeing here, this hyperbola. This is the next hyperbola where y is equal to 2 pi over x. Anyway, I'm taking slices to try and figure out what this looks like. Let's put it back to what it was at -3 and 3. And there's no breaks in this curve. It's a continuous curve. It's smooth as well. There's no sharp points. In single variable calculus, having no breaks means it's continuous, means the limit exists. In single variable calculus, being smooth means the derivative exists. So visually, it looks like the limit exists everywhere here and the derivative exists everywhere here. Algebraically, yeah, because sine is a continuous function. X times y, there's no dividing by 0 or square root or anything, so this is a continuous function. One example of what what we're going to look at more deeply in this chapter. Things to think about. Well, we've got range and domain. The domain then are all the x's and y's, the input variables, and in our case here, the domain is all of R2, because I can plug in any x, y point. I can take the sine of any value. The range are all the possible z's, all the possible heights, all the possible outputs that can be. And we can see that when I take the sine of any number, you can't get anything bigger than 1, and you can't get anything smaller than -1. So the range is the one-dimensional set from -1 to 1. So this is we're in 3D space. So 3 dimensions. I use 2 of them for the domain, the x and y, and I use 1 of them for the range, the z. The domain then is all of R2. The range is the interval, the closed interval from -1 to 1, because -1 and 1 are included. Let's look at some more, well, I was going to say more interesting. That was an interesting function. Let's look at some other functions. We want to find the domain and range of this function. So let's draw it first. Should we draw it? No, let's answer the question first and then we'll draw it. See if the drawing confirms what we wrote algebraically. Now, domain is an easier question. It's an x and a y that we're plugging in. So the domain is a two-dimensional set. And let's think about the things we can't do. You can't divide by 0, and you can't take the square root of a negative number. So this xy minus 1 has to be strictly positive. Can't be 0, can't be negative. That's giving me the curve. If I solve this for y, that's going to be y has to be greater than 1 over x. So when y is equal to 1 over x, I'm getting that hyperbola. Y has to be bigger than that. It's not equal. So when I draw this in 2D, that's going to be a dotted line. But let's take a look here. Is there anything else that we have to worry about? Well, don't divide by 0. Don't take the square root of a negative number. We got that in that one statement. What about don't take the ln of 0 or a negative number? No, there's none of that. The top here, the numerator, that's just a polynomial. That's allowed to be 0. So there is no, I don't see any restriction on here for the domain. So it should be that y just has to be bigger than 1 over x. How do we express that? Well, it says find here. Lots of times it says sketch, like in the question coming up. So we could write this domain as in set notation. So is equal to the set of x, y points such that this is true. And you can even add, x and y element of R2. Let's put that in there. Now, we know that there is an element of R2. So we could write that as in set notation. We could also draw it, and sketching it is a more common way of expressing it because it's easier. So if I'm sketching it, I'm going to look at, here's our xy plane. So the z is coming out of the board. And if I draw this hyperbola, if I draw the equals, but I'm making it dotted because I'm not allowed to be on it. So that's this dotted curve here is the y is equal to 1 over x. Now, that's the boundary. Do I want to be, what side of the boundary do I want to be on? Well, this is the, let's try a point over here. This is the point, I don't know, 10, 10. Does 10, 10 satisfy it? 10, 10 minus 1 positive, yes. So this region is included. Minus 10 does satisfy, so this region is included. What about in here? Well, 0, 0's in here, and that does make, that's not in the domain, so now I'm not including this middle boundary. So there's a sketch of the domain. Domains are the easier one because we know what we're doing with that. We're just don't divide by 0, don't take the square root of a negative number. What about the range? The range is a harder question. Can I get 0 out of this? Well, yeah, if I make x equal to 2, y equal to 1, that works. I get out 0. Can I get negative numbers? Yeah, if I make, so the denominator is always positive. So if I make x less than 2, magnitude less than 2, the top is negative. So I can get negative numbers. Can I go all the way to negative infinity? Yeah, because I can make this, I can make the y like a zillion, and I can make the x 1. So that would be minus 3 divided by a zillion, which would be like minus 3 divided by a zillion would be negative but close to 0. Oh, if I want this whole expression to go to negative infinity, I need to divide by something really small. Oh, so I basically need to get super close to that dotted boundary. If I get super close to this dotted boundary, the denominator goes close to 0. So dividing by something close to 0 is going to give me a huge number. And as long as the top is negative, it's going to go to negative infinity. If the top is positive, then I'm going to go to positive infinity. So I'm arguing out here that not that one. I'm arguing out that the range of this is all the reals. So z can go from negative infinity to positive infinity. So here's another example. Now this one, z is equal to 3 minus x squared minus 3y squared. If we talk about the domain, and they want us to sketch the domain, this is all polynomial. So there's no dividing by 0 opportunity. There's no lns in there. There's no square roots. So the domain is all xy points. So sketch the domain, yeah, I don't want to do that because that's just going to have me coloring in all of R2, coloring in an infinite plane. We don't have time for that. But let's think about the range then, because that is something of interest. What's the range? That's a better question. If I were to sketch this, oh, we recognize this form from a previous video, right? It's a paraboloid. So I know that it's going to be either an upward facing paraboloid or a downward facing paraboloid. So we want to talk about the range here. Let's rearrange this. If I make this, I'm going to bring the x squared and the y squared over to the other side of the equals. I'm going to rearrange this equation to make it more clear here. So I'm going to make this x squared plus 3y squared is equal to 3 minus z. Now, every time you pick a z value, every time you pick a z value, you're taking a slice at a height, then you're getting x squared plus 3y squared equals a number. That's an ellipse, conic section. So, but x squared plus 3y squared is a positive number. So right away, 3 minus z has to be positive. So z has to be greater than or, no, z has to be less than or equal to 3. If I put in a z bigger than 3, then I've got something squared plus something squared is equal to a negative number. So here's our range. Now, okay, we answered the what's the range. This is this is one graphing of it. Let's make a better picture using that DP graph. So 3 minus x squared, x squared, I'll do it this way. X squared plus 3 and let's open our viewing window. Yeah, there's the tip of our paraboloid. The height, the range, the output, the z is always less than or equal to 3. Each one of those slices is going to be an ellipse. And that's what I want to talk about here then. I want to talk about level curves. So sketching the level curves when z is equal to each one of these values. Let's do that. Okay. So I'm just looking in the xy plane, And I'm going to use this form of the equation here because it's easy for me to think about. When I make z is equal to 3, that's x squared plus 3y squared is equal to 0. That's just this dot. That was the tip of the paraboloid. When I make z equal to 2, that's x squared plus 3y squared equals 1. So that's a ellipse. Okay, that's the z equals 1 ellipse. When I make, no, that's the z equals 2 ellipse. The z equals 3 is just a dot. The z equals 1, the ellipse is getting bigger. Z equals 0, the ellipse is getting bigger. Minus 1, that's going to be 3 minus a minus 1, that's a 4, so that's an even bigger ellipse. So even if I didn't look at this equation right away and remember, oh, that's a paraboloid, we could think about taking slices of it, level curves, and figure out, what does a stack of those ellipses look like? Oh, it looks like a paraboloid. Now, let's take a look at, if I look straight down here, then it's kind of like I'm seeing my level curves here as I was sketching. And one thing I notice is that the level curves are, there's the tip. That's the z is equal to 3 level curve. Z is equal to 1. So big step, smaller, 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 smaller. Out here on the edge, the contour lines are I call them contour lines. The level curves are very close together. That's the next thing I want to think about here, this question. What does it mean when the contour lines are close together? Contour lines is a phrasing from when you look at maps. So what does it mean when contour lines are close together? So let's just, over here, I'm going to draw contour lines on a map. So here's the elevation of, that's 1,000 feet above sea level. Here's 2,000 feet above sea level. Here's 3,000 feet above sea level. So when the contour lines are close together, that's 2,000 to 3,000. This is, if I'm climbing up this hill, this is very steep. So if I wanted to get to the top of this mountain, it would probably be a nicer walk to take it this way, because the contour lines are far apart, so it would be a nice gentle stroll up the mountain. If you wanted to do some crazy mountain climbing, you take the hard route this way. So as far as what is our question, what is the answer to our question, what does it mean when contour lines are close together? The hill is steep. What does it mean when our level curves are close together? That's where the function increases in height quickly. It's steep on this side. And later on, we're going to want to think about these 3D curves as hills upon which we're walking, because it's going to make the math make more sense if we think about that. Especially, put this in the back of your head, when we get to the gradient vector section. So 2D, we can think about it as mountains. What about functions of more than two variables? So here I've got z as a function of f, or as a function of x and y and w. So it lives in four-dimensional space. The domain would be three-dimensional space. The range would be one-dimensional space. So three-dimensional space plus the one-dimensional space combined together to give the four-dimensional space that this object lives in. Now, what is this? I don't know. It's hard for me to imagine. We can talk about range and domain, though. Domain is all the x, y, w points I can put in. The domain would be a subset of R3. subset of 3D space. It's all polynomial. There's no dividing by 0. There's no taking the square root of anything. So you can put any x, y, w set in there, triplet, as we would say, in there. So the domain of this function would be all of R3. What's the range? Well, I can get out 0 if I make x equal to 0 and w equal to 0 and y equal to 1. I can get out 0 for z. Can I get all the positive numbers? Yeah. Just make, if I make y equal to 1 and w equal to 0, then I can make x as big as I want and get all of the positive z values. Can I get all the negative? Yeah. Just make x is equal to 0, y is equal to 0, and then make y bigger and bigger and bigger and bigger, and I'll get all the negative values as well. So this function, domain is all of R3, range is all of R. So z can go from minus infinity to plus infinity. What does this look like? I don't know. But I do know what it would look like if I write it like this. Because now if I take level curves, I'm setting z equal to a number. If I set z equal to a number, then this is a hyperboloid of, because there's one minus sign, a hyperboloid of one sheet. Oh, that's if I make z equal to, so that's if this side is positive. So go back to your quadratic surfaces video to think about this. If z is greater than or equal to 1, then this side is positive, and that makes the level curve a hyperboloid of one sheet. What if it's less than? Like, what if this side is negative? If it's negative, I can multiply the whole thing through by a negative number and get two minus signs over here. So it would be a hyperboloid of two sheets. These are just the level curves, though. That's analogous to the ellipses, are slices of this 3D shape. Here I've got a hyperboloid of one sheet, a hyperboloid of two sheets. The level curves are 3D shapes that we recognize. Now, we talked about, oh, this is a paraboloid. Think of stacking a whole bunch of these ellipses together and you would get that paraboloid shape. Yeah, okay. But in four-dimensional space, think of stacking a bunch of hyperboloids of one sheet and then of two sheets together. I can't think like that. I don't know what's going on with that. So we're going to have to fall back upon the algebra to figure out what's happening with it. I guess my point here is that we can have this sort of thing. Now, you know, such a thing exists in mathematics, and you might be saying to yourself, well, okay, things exist in mathematics, but what good is that of me? It's not even a real thing. I don't live in 4 dimensions. But we can have 4-dimensional functions that have significance to us. What if, and I'm going back to this function, I'm going back to the original formation here, a function of x, y, and w. What if the x and the y and the w were coordinates in the room you're in right now, right? You'd have 3D coordinates. You'd have your x point along the floor, your y point along the floor, and your w up. So you could plug in, take a reading of any place in the room that you're in. What's the output then? Well, say you start a fire in the room that you're in now, but start it in the corner. Now, wait for a minute. The room's starting to fill with smoke. The density of the smoke is greater higher up than down below. Its density of the smoke is greater closer to the place you started the fire. So the density of smoke is a function of your position in the room. The position in the room is given by a three coordinate x, y, w, x, y, w. So then the density of smoke, the output, is given by a function in 3D. So they do have bearings, right? You would think about this 3D density of smoke, and you would want to move, solve this function for where it's the minimum and go to that place in your room. Now, just like in other videos where I ask, say pause the video and do this example, and I think, some people do it and most people don't. I hope that everybody didn't start a fire in their rooms. Anyway, we'll end the video. Go take care of, if there's a problem, an emergency, a fire, you can take care of it now.